Check, check. All right, we'll get started right away. So, thank you so much for coming to my talk, The Journey of a Dotty Diagnostic. I want to first of all say that I'm very excited to be here. This was actually the first conference, or like in-person Scala conference I ever came to back in 2018. And it was just when I was starting to learn Scala, and I had just started programming a couple years before that. And my wife told me right before I came here, do you remember when you came back from the conference and you told me how confused you were with everything? So I'm happy to say that like 4 years later, I'm only confused like half of the time, but the confusion level is definitely going down over time. So hopefully today I don't confuse anybody. Everything's pretty simple, I think, today. But let's talk a little bit. But if you're unfamiliar with who I am, first of all, most importantly, I'm a big NeoVim fan. That's actually how I got involved in like some of the tooling ecosystem I work in. So if you are a Scala developer and a NeoVim user, you're the best. You'll find me working kind of around the Scala tooling ecosystem, most notably, I guess, known for working in metals. I have a podcast called Tooling Talks, where we talk about, all sorts of tooling related to Scala. And I'm a software engineer at Lunatech, which is my t-shirt. And you can find this talk on my website under Talks, and there'll be a bunch of different talks listed there. So today, I want to talk about this thing. I want to talk about diagnostics. And if you are anything like me, when you hear a talk about diagnostics, the first thing you think about might be why. That sounds kind of boring, not like the most interesting topic, and who knows what we'll even talk about. And hopefully today we'll go through all of these sorts of things. We'll talk about why diagnostics are important, how diagnostics actually get to your editor, and a whole bunch of different things related to diagnostics. But before we can talk about that, we kind of have to have a common understanding of what is a diagnostic. Again, kind of a simple question, but it's maybe a little bit more involved than we might originally think. Another way to state that is rather what makes up a diagnostic. When you think of a diagnostic, what do you actually think about structurally, and what is actually part of a diagnostic? So we'll have some very simple examples. And the first one you can see here is just val word, which we say is a type string, and it equals to 1. And you don't have to be an expert at Scala to know that this will not work, right? So in your editor, you'll see something like this, where you will have an error, and you'll be able to hopefully fix your code. But when you see something like this, let's kind of like dissect it a little bit and look at the different parts of the diagnostic to get a better understanding of it. So first of all, you have a message, right? And that's right down there. It should hopefully tell you what's wrong with your code and maybe some other stuff. But in general, a message is just part of a diagnostic. Secondly, we have a severity level. And in this case, it's an error. And there's normally different indications about why it's an error. It tells you that it is an error. And in my case, in my editor anyways, I see a little red check mark or red dash, and I can see that the message itself is red, indicating that it's an error. If it's a warning, the color changes, and now I can see orange, right? So I know that these are all warnings. And now we have info, and this is getting a little bit more interesting, right? Because this is still called a diagnostic, but it's not something that's wrong necessarily. And this is actually an example from Quill, because there's not many libraries in Scala that actually make use of these. And this is like one of the coolest things ever, is that you have a query here in Quill, and there's actually an info diagnostic, indicated by blue, that will show you some related information to this diagnostic. So not something wrong, just extra info for your code. There's actually other types of diagnostics as well, like a hint. What are they in Scala? I have no idea. We don't really use them in Scala, but they're there if we ever want to use them in the future. So the third part would be a position, right? If you have an error, you also want to know where it is. And again, indicated by the thing on the left, which will show you what line number it's on. I don't use line numbers, that's why you don't see a line. But it will also show you what character actually it's on. And this might not seem like a huge deal, like that I'm specifically on the 1, but this will matter a little bit later when we dive into other parts of diagnostics, because if I look at Word, for example, there's not a diagnostic attached to Word. It's only attached to the 1, and that will become important later on. So based off of what I just covered, I created what I call the Diagnostic Usefulness Scale. And on the far left-hand side, we have no help. Doesn't help you at all. On the right-hand side, we have all of the help. But in reality, like the left-hand side is not really actually diagnostics at all. And in the middle where we have is what I just showed you, right? The core parts of a diagnostic. We have a message, a severity level, and a position in your code where it is. But again, the left-hand side is not really practical, so let's throw it away. So the usefulness scale now looks like way on the left-hand side, we have the core parts of a diagnostic, or the very basic parts of a diagnostic. And on the far right-hand side, we have all the help. And what we're going to talk about today is the middle. Okay? And there's a few questions we're going to ask. Where's Scala on this scale of usefulness? Is it on the left-hand side or right-hand side? What else is on this scale? And sort of related to that question is, where are other languages on this scale, and maybe how does Scala compare to those languages? So the first question, where is Scala on this scale? In order to answer that question, we have to dig into diagnostics a little bit inside of Dotty. And for the most part of the talk today, I'll focus on Scala 3. And we have to answer this question first. So another way to phrase the question would be, well, how does the diagnostic get from the compiler to your editor? And you sort of need to understand this as well when we look at what makes up a diagnostic. So maybe seems a little unrelated, but we'll get into it. And the answer is, well, it all depends. Like, it depends. Why? Are you in the REPL? Are you using X build tool? Are you using a build server, maybe? Are you using IntelliJ, Metals, Enzyme? Or a combination of different ones of these. And like the arrows would go all over the place about what your actual diagnostic message looks like based on all of these things. So I drew a little diagram here to help us out. We have the compiler, then we have a build tool or a build server. We have Metals, because I'm most familiar with Metals, but for more or less it will work somewhat similar in other editors. And then you have your editor, and we'll break these down. So let's start with the compiler. So how does the error actually formed in the compiler? And it's done different ways. So in some ways, and these are like real chunks of code from the compiler, so all the links on the bottom, if you're looking at the slides, will actually bring you to those parts of the code. So in some examples, we have just errors that are reported right on the fly. Like we do nothing special. There's no creation of a diagnostic or a message. We literally just have a string and a position, and we say, hey, report this. Like, easiest way. Under the hood, it actually creates a diagnostic and does some other things, but this is, I would say, from what I saw, the most common way to report a diagnostic in the compiler. There are other cases where we report something called a message. It's a little bit more structured at this point and has more things attached to it, and we just pass it to the reporter and say, hey, report this message. So let's take a look at some of these a little bit. First, we have a message. Well, what's all in here? It's kind of small, but I'll go through it. Honestly, pretty much everything in here either returns another message or just returns a string. So when you think of message, you can think of it as just what you end up seeing as the actual error message. And then you'll see way up on top inside, there's one parameter, val error ID, which we'll get into a little bit later. Well, then we have a diagnostic, and a diagnostic contains a message and the source position and a level. And if we looked at what the core parts of the diagnostic were earlier, you'll recognize these three things as the core three things that make up a diagnostic. And then you have some other few things on the bottom, like some helper methods, I guess, and some things about positions, and sometimes there's weird things in there that you want to strip out or verbose things, but we'll get into all that stuff later as well. So we have our diagnostic, and where it goes next sort of depends on two different things. Is it something that's using zinc, and you may think, like, why is zinc in the picture now? Like, how does that get into this? Or something else, okay? And first we'll talk about zinc. How many of you have actually looked at the Dotty code base, out of curiosity? Like 3 people, okay. Okay, so if you are ever going to look at the Dotty code base, you'll notice that there is a directory which might confuse you, because it confused me when I first saw it. And it's called the SBT bridge. And in my head, I was like, well, why is SBT-related stuff in the actual Dotty compiler? And you'll see a couple things. First of all, you'll see a resources directory that has a compiler interface too. And if you actually look at the Zinc documentation, you'll see this quote. The compiler bridge classes are loaded using Java util service loader. In other words, the class implementing blah, blah, blah compiler interface 2 must be mentioned in a file compiler interface 2. So that's how Zinc knows that this is what implements the bridge. And we have on the bottom XSBT, which we can ignore for now, I guess, because that's related to the old versions of SBT, or old versions of Zinc, rather. But what we want to focus on is this big chunk in the middle. And this is actually, like, when all the pieces came together for me, it blew my mind a little bit. And that's what we're going to go over, is basically the journey of how this thing, starting in the compiler, gets all the way to your editor. And the middle part is what needs to be implemented in order for any tool in the Scala ecosystem using Zinc to report an error, or to report anything, actually. So it's really important, and that's what it is. So it says SBT bridge, but really it's related to Zinc. The only reason it's called SBT was because Zinc used to be part of SBT, so there's a little bit of naming confusion going on there. Okay, so let's dig into this code a little bit. And the first piece of code we're going to look at, it actually belongs in a repo called SBT interfaces, or rather it's a module in SBT called SBT interfaces. And if your gut reaction is, well, if we're talking about diagnostics in the compiler, why are we starting in SBT? And again, if you're using any tool that uses any type of interfacing with Zinc, we have to start here. And this Java interface is, again, probably pretty familiar to what you think it would look like based off of what we went over. But we have a category, a severity level, a message, and a position, and then rendered. And rendered will come into play a little bit later, but it has to do with rendering better diagnostics or more useful diagnostics. So we have this problem here in SBT. And in order to better understand this a little bit, remember our nice diagram where we have the journey. The arrows actually represent specific interfaces or protocols. So the first one, whoops, oh, I guess I'll go into that later. So forget that I said that. So here's our diagram again. And this was just to show you where we're at. So we were in the compiler. Now we're going to go to the build tool. Or rather, Zinc is more or less part of your build tool. And the way that the diagnostic moves forward at this point in time also depends on a couple different things. Are you running it with the tool itself? So are you running SBT compile or mil compile? Or are you using BSP, which is the build server protocol? How many people are familiar with BSP when I say that, by the way? Is that somewhat well known now? I feel like SBT creating a BSP directory just made everybody aware sort of what BSP was. So what I was just talking about with the arrows meaning something, the first arrow between the compiler and your build tool / build server is the SBT bridge, because more than likely, again, your build tool is using Zinc as an incremental compilation, so you have the SBT bridge. Between your build tool and a language server like Metals, you have something called BSP, which is the build server protocol. And then between your language server and your editor, you have something called LSP, which is the language server protocol. And how many are familiar with the language server protocol when I say that? I feel like also somewhat popular. If you're using Metals, you're using this exact chain, basically. So let's look at how diagnostic actually looks like in the protocol, because ultimately, if where we're ending up is using LSP, that's sort of what the end user is going to see. So this is what a diagnostic looks like according to LSP, and therefore BSP, because they mimic each other. We have a range, which is a position. We have a diagnostic severity level. We have a code description and a code. Okay, so that's something new we haven't seen before. What's the code? So we can maybe put a big question mark on those. We have source, which is where is this thing coming from? We have a message, which again we've seen before, and then some more new things that we haven't seen before. A tag, related information, and data. So hopefully you're wondering, like, what are these other things used for? Does the compiler use those? Now let's jump to SBT finally. So we have the compiler that reported some error. It was implemented by the SBT bridge and therefore reported to your build tool, which was using Zinc, and now we finally are in your build tool. So we'll use SBT as an example, and remember when you saw the two arrows, one of them using the tool and the other one using BSP, we'll focus on BSP. So how does this get reported via BSP? So up on the top, you see one parameter, problem, which is the interface that we saw early on. And you see some pretty SBT-ish stuff. We are just getting we're basically taking the problem and creating a BSP diagnostic out of it. So BSP diagnostic. So our original problem that we saw earlier turns into this, basically. And then at the bottom, you'll see publish diagnostics, and it sends it to the language server. So now we're at the language server. And for this case, we'll use metals as the language server. And in here, you see a absolute path, which is the file that you have open. And then you have a queue of diagnostics. And then you see some related code, some of it having to do with deduplicating, making sure you're not reporting the same error twice, and ordering sometimes. And then way at the end, you have language client, published diagnostics, new published diagnostic params. And now, finally, you have the diagnostic in your editor. So to recuperate, or to reiterate, we went from the compiler, we went through the SBT bridge, we went into your build tool translated this problem into a diagnostic. That diagnostic was reported over BSP to your language server, and then your language server took that and forwarded it to your editor. So it goes through quite a few things in order to actually get to where you're seeing it. So now that we have kind of seen the actual structure of what a diagnostic looks like from the compiler all the way to your editor, where on the scale does Scala sort of fall? I would say more or less, if this was the scale, Scala kind of sits way over here because it implements the bare minimum of what makes up an actual useful diagnostic. But wait a second, maybe that's not fair. Maybe there are some more steps to this, right? And we will use another simple code example for this. So if you, again, are familiar with Scala a little bit, you'll know that this won't work, right? You have unimplemented members. So if you run it with, in this case, mil, you'll see an error like this, and the compiler will actually report to you like, hey, I cannot create greeting because there's two unimplemented members here, goodbye and hello. And I'm going to help you a little bit, and I'm going to tell you exactly what you can do to get your code to compile. And it tells you basically inside of a comment there. That's pretty nice, right? Here's another example. This won't work. You don't have to be super familiar with inlining, but just know that this won't work, and there's going to be two things reported here. You're going to have your actual error on top, which is no given instance of type foo string. And I'll go back here just for 1 second in case you want to look a little bit closer at the code to understand that. I'll jump back again. But then below we have what's called your inline stack trace, which should, in theory, point to the two inline methods or the two things that were inlined. And this is extra information that's pretty nice to have, especially, these are really simple examples, but imagine a more complex application with inlining all over the place and things, that becomes pretty useful. So maybe taking into consideration, the other thing you saw up above of, maybe some default implementations that it provides you, and this case where it's actually giving you some more information about where stuff is inlined, it'll be a little bit more helpful. But notice that in your editor, that same nice error that you saw here where they had extra information about your inline stack trace, when you're in your editor, you don't actually get that. You just get a plain message again. Well, most of us on our day-to-day jobs, as we're coding Scala, we're inside of an editor. So this is the editor. This is the error you're probably going to see, not the fancy one. So with that in mind, let's scoot Scala over a little bit, right? It does a little bit more than the bare basics because the messages are more helpful and they help you in more ways. But what else is there on this scale anyways? What's basically between where Scala is here and all of the help? And another way to phrase this question, or you can't really answer this question without also answering where are the other languages on this scale, because they're related to each other. And we'll use other languages as an example to show what else could be on this scale. So we have another really simple example. Val greeting equals hello, and then greeting equals hi. And again, you'll probably know that this won't work, so you'll get an error from Scala. And your error here, and I'm using VS Code in this situation just because it makes some of this stuff really clear. You'll see the error message, reassignment to val greeting. You actually see a little bit more information that doesn't come from the compiler, but it comes during the creation of the diagnostic in the build server, bloop, and that's why you see the little grayed out bloop area. And then that's it. And then the position you'll understand is underneath greeting, and that's kind of it. So that's sort of what you expect. It's helpful. You know you have an error. But you might ask some questions when you look at this that aren't obvious at first thought. Well, where's the original assignment? I know that I'm reassigning this, but where did I originally make this mistake? And again, the example I showed you was simple. It's 3 lines long, but imagine a very large code base. Can I get an explanation of this error? Again, really simple example, but as you progress and as you have more complex diagnostics, you might wonder, well, I see this error message, but I don't really understand what it means. And then what are my alternatives? Like if I ran into an issue, how do I fix it? Or what can I do differently to fix these things, right? So let's look at a different language and see what they do. Here's Rust. Again, you don't have to really know Rust to kind of understand the code. It's the same exact code that we had in Scala. And let's look at the error message that Rust gives you. And we'll notice quite a bit of different things right away. And let's look back at the questions that I just asked you. So where's the original assignment is the first question we asked ourselves. Well, Rust does a pretty nice job of saying, well, actually, your first assignment to greeting was on line 4, character 9. So, pretty nice. That's extra information we didn't have before when I was looking at the Scala one. Well, can I get an explanation of this error? Maybe I'm brand new to Scala or any programming, and I don't understand immutability, and the idea of reassigning a variable doesn't really make sense to me. Well, Rust says, oh, okay, cool. You can't assign a variable. Here's a link, E0384. And I'm curious at this point, if any of you are using Scala 3 in the shell or in the REPL, if you've ever noticed at the top of your diagnostic, every once in a while, you'll see like E038. And have you ever wondered what that was? Has anybody noticed that or no? Like, I'm curious. So like nobody even notices it hardly. So every once in a while, you will see this reported. But as far as I know, there's no public information ever out there about what that actually means. And it's the same thing that Rust is sort of doing here, is that it's a unique error code associated to that diagnostic. And what does it do? Well, it leads you to an error codes index page, of course. And this error code has an explanation. It has some code samples. It even has a little run button that you can run the example, and it will show you exactly what the error is. So pretty helpful for a newcomer, right? Like if I'm new to Rust and I don't understand the error message contains a clickable link that brings me to a nice documentation page with runnable examples that I can see exactly like what the error means. Pretty nice. So let's move on to the next question. Well, what are my alternatives? Like okay, so I understand I can't rename greeting in this sense, but in my code, I really want to. Like that's what I'm trying to do. I'm trying to rename it. Well, it has an answer for that too. We'll consider making this binding mutable. Change it to mutable greeting. And then a bonus, what if it just did it for you and you didn't have to do it yourself? And in the Rust example, if I went up to the first position of where greeting was, I see something called a quick fix that just let me click a button and it will automatically change the code for me and make it right. That's pretty awesome. So let's look at another example, Elm. And the reason I picked these two is because anytime you ever ask people, like, what are the best languages for error reporting? Like, you will always get the same two answers, Rust and Elm. Elm does do a really great job of reporting errors here. Like you have multiple different positions. You have some other information maybe. But do notice that there's no structural information. You don't have anything you can click on. It's just a big string. So maybe the string is more helpful in your editor. But in reality, Scala kind of has the same thing. So I thought Rust was way better at it than Elm was in terms of structural diagnostics. So if this is our scale again, and that's where we have Scala, I would more or less put Rust a little bit more on the other side of all the help. Still not everything, but until something can code fully for us, I don't think we'll get there. Well, why is this? Like, why does Rust do a better job with this? Why doesn't this happen in Scala is what you might be asking. And we have to kind of return back to the idea of the structure of a diagnostic. And here is where it's defined for Rust. And you'll notice message, no surprise again. And now we have code built right in, which is an optional diagnostic code, which is what you saw in the clickable link. That brought you to a page that defined what the error was. And then you have spans, which is not super clear yet, but we'll look at it. You have level, which is, again, same thing that we had with severity level. You have children. Oh, so this is another new idea. We can have diagnostics that have other diagnostics, where in Scala, you didn't have that. Then you have rendered, which is sort of the same thing that you saw in the SBT example. Well, let's look closer at diagnostic code. So code has a code itself, which is a unique identifier, unique to every diagnostic that Rust reports. Then you have an explanation to that code, which is pretty helpful, right? Now let's look at the other part that we said we noticed, the diagnostic span. So this is more or less just position with a whole bunch of other stuff. So notice we have a whole bunch of information about where this starts, where it ends, but then we find some really interesting stuff. We have is primary, meaning like, is this the actual point of the error, or maybe is it another diagnostic related to the core error? So if you have, multiple different errors where one is the one that's actually causing all the issues, we can signify that. We have a label attached to it. We have now another new thing, a suggested replacement. That's crazy. So if the compiler knows how to fix this, it can suggest something structurally when it reports that diagnostic. And it has a suggestion applicability, which means, will this fix your error or will it not? Will it maybe fix your error? Well, let's give it a lower applicability level. So then other tooling that's maybe using these can decide, I can apply this no matter what, and it will work. Or maybe I can just give this as a suggestion and tell the user this might work. So that's what the applicability is. And there's some extra macro stuff in there as well. But this isn't just Rust that does this either. If you look at Clang, for example, they have something called fix-it hints. And this is taken right from the documentation. But fix-it hints provide advice for fixing small, localized problems in source code. So when Clang produces a diagnostic about a particular problem, it can work around, such as non-standard or redundant syntax, missing keywords, common mistakes. It can also provide a specific guidance in the form of code transformations to correct the problem, which basically means it can fix it for you, and it will send it right to you to use. Well, what about a compiler error index? Again, we mentioned this before. This is another thing that it has, right? So we have a whole huge list of all these different diagnostics. Let's check 576. And again, we have specific examples. This is really nice to have, okay? Okay, but there is some progress being made here. So we went through a whole bunch of other stuff, and at that point you might be thinking Rust is so much better, all this stuff. But that's not really necessarily true. And we want to look at actual use cases for this, right? Because theoretically maybe we can see Rust has all this cool stuff that it's doing, but what use is it actually? And this is part of the Metals code base where we have a refactoring where if you have something like you see here, where you have a return type that's maybe int, but you found a string. And if you're like me and you're doing a bunch of refactoring and you have explicit methods, sometime you may have annotated something explicitly in the past, you change your code and you mean to return a different type, but you just haven't changed your explicit return type yet. So that means you delete the explicit return type, you change the expected return type, and then your code compiles, and you're happy. Well, in Metals, we thought, well, we can help you with that. We'll just produce a code action that will automatically change the return type for you. But when you start to do stuff like that, you have to recognize the actual diagnostic that you're on. And the way that we do that in Metals is we literally have to get the diagnostic message, re-regex the message, we identify what diagnostic it is, and then we can offer stuff. And you start to realize when you see tooling doing stuff like this that when you're handling diagnostics in Scala, there's literally no way to handle them apart from trying to regex the error message, because at the end of the day, the only really useful information you have is just a string. So there's nothing else there. And we have made some changes. So you may have missed it early on, but when I showed this before, the problem that is in SBT interfaces, I put old, because this has actually changed already. So this is what it looks like now. There were some changes that were made. And you see now in the core interface, we have a diagnostic code, just like you saw on the LSP BSP1, which is a unique identifier. And we also have diagnostic related information, which is related information to that diagnostic. But as I said before, when we went through the entire chain of stuff, it took a long time to do it because there's changes necessary in everything. We had a pull request to SBT and Zinc because once we bumped it in the interfaces, we had to release it, and then Zinc had to update to that new released version, and then we had to release Zinc, and then we had to update the SBT bridge in Dotty, and then we had to do some more changes in Dotty to make sure the error messages were being reported correctly. Then there were changes in BSP because it wasn't up to date with the LSP spec. Then we changed the SBT server. Then we changed the Bloop server. Then we changed the Mill server. And then we finally changed Metals. And finally, at the end of all of that, we had one small little change that says when you get your diagnostics on your editor, you get one new field, code 7. Awesome. So a ton of work just to get like one tiny little piece of information, but it goes to show that like the diagnostic journey from the compiler to your editor actually goes through like a whole ton of stuff. But now for tools that are trying to use this, they have a unique identifier, and there's no longer any necessity to try to do like regex on diagnostics to do useful things with them. There's some other cool examples that are being done in the ecosystem as well. So how many people are familiar with Scala CLI? I feel like most people have heard about it maybe now because you see it referenced all over the place. So Scala CLI has been doing some really cool stuff with this as well. If you're a Scala CLI user and you have a using directive, like you see here, using lib, oslib 078, you can actually run Scala CLI like update dependencies or something, and it will, in the terminal, show you like, here's the directives that you have that are outdated. But if you're in the editor, you kind of want that same functionality, right? So Lucas from the Virtuous Lab team just merged a really good example of this, that when you're in your editor and you have a using directive, in the next release of Scala CLI, you'll see this. You'll actually get a quick fix that will just say, hey, this is outdated, do you want to update it? And you'll just click it, and it will automatically update the dependency in your file. That's pretty cool. I would wish we had way more things of that. And if you look under the hood at what this looks like, you have, again, your diagnostics that are being returned. You have a range of where this diagnostic is, severity. So severity 4 is just info, so it's extra info that you can have. You have an error message, a source, Scala CLI. Then you have this extra field, which we saw way early on, but we haven't talked about yet, which is data, which is just extra data that can be persisted by the client to do something with. So in this case, it also has a position, and it has new text that can just be applied and updated. So if you're following that line of thoughts, you may be thinking, well, what if instead of this error that we had before, where we saw that this couldn't be implemented, and then we see the compiler like knows how to help us. Like it knows that you just need these stub implementations to get your code to compile, but it's just in a string, so you can't do anything with it. But what if instead, and again, this is what that error looks like under the hood, you just have, again, range, severity, error, source, it's coming from bloop, and then message. And this message has like everything that we want in it, but again, it's just a giant string. But what if it instead looked like this, where you had, again, an extra data field that has a range of where this stub implementations could go. Then you have some new text that an editor or a tool could just click, and it would be applied and automatically fix your code for you, basically. And what if we could reference something like this? And this is a small project that I've been doing on my free time when I feel inspired but haven't worked on it much lately, is the same thing that you saw in Rust. So for every error, and you can actually see it here maybe, you see, like this is the example I was telling you about, you see E001 that's reported, and that's the unique identifier, because for a long time, I think since the beginning, Dotty actually had error, like unique error codes, but they were never reported or used half the time. Because in the very first example that I showed you where it was just like a string being given to the reporter in a position, that actually reports -1 as an error code. So there is no useful error code. So changes would have to happen in order for that to be useful in the compiler. But what if we had something like this that users could reference? If you're a newcomer to Scala and you hit on an error that you don't know how to fix, and you could go to something like this and have the error explained to you. You could have a runnable example. It could show you exactly how to fix it. That would be pretty cool. And there's a lot of other things that we could do with this as well. For example, you saw the diagnostic related information. If you remember the inline example, which is this code, you saw some big string of ASCII box that said, like, you have inline code at these positions. But if we change the structure of how those were actually reported from the compiler, you could do something like this, where you hover on the actual error, and you could click on the other parts of your code that are inlined. And again, this is like a really simple example, but imagine a giant code base that has random inline code, and you have some type of diagnostic, and you could actually hover on a diagnostic and jump to other parts of your code that are related to that diagnostic. That'd be like a much better user experience than we currently have. You can track the progress on almost all of this. So there's a giant issue here in Dotty, which maybe I'll actually click just to give you an example. or not, because it'll have to maximize my thing. But if you go to this issue, you'll see sort of like all the steps that I outlined of where things need to change. And you'll see that progress has been made on the diagnostic code part all the way through the chain. Now it's time basically to implement the related information, which would unlock the thing I just showed you here, to do this sort of stuff. And there's other examples in Scala that this would benefit as well. So there is progress being made here. You can follow it here. And then hopefully, as users start to benefit from these things, there'll be more incentive to do more of this stuff in the compiler to make sure that when we're reporting errors in the compiler, everything has a unique identifier. Also, when we're reporting errors in the compiler, any related information about inline code or other things could be reported in a structural way. Then maybe stretch go away in the future. If the compiler knows how to fix something, it could just give that to you structurally as well, so that users could just click it and it could be applied and fix your code. Because right now, we are sort of forcing on all tools to regex error messages, recompute how to fix things, and do them when the compiler might know how to fix them. And that's it. Thanks for listening. We do have a couple minutes if anybody has questions about diagnostic stuff. Yeah.
Just a question, because ScalaFix also has Diagnostic in its library. What's the differences currently between the two? Or if ScalaFix Diagnostic would also catch up with what you've done in Dotty?
By ScalaFix Diagnostics, do you just mean like the rewrites that ScalaFix can do?
You have the rewrite, but you also have the linter diagnostic that you can publish.
To be honest, I'm not super familiar with it. I know ScalaFix has diagnostic stuff that it can report. So in theory, it can do the same thing that Scala CLI did, right? Like how it had a data field and new text and a position. In theory, ScalaFix could do that and could report it in the same manner, and then tools could apply it. Like, long story short, when the idea of metals was first created, or when we first started metals, the impetus to it was that they wanted diagnostics from ScalaFix to be shown in the editor. Because right now, if you're a ScalaFix user and you want to run a ScalaFix rule, you have to like literally run either the CLI or the SPT plugin. Where the idea was to do that right in the editor and probably do exactly what you're referring to. Mm-hmm. But like 4 years later, we've never implemented the original reason metals was sort of created for. But in theory, yes, it could happen. Yeah.
Okay, thank you.
Yeah. A couple more. I'm nervous about Guillaume's question.
So you had this example where metals parses with a regular expression to find the found and expected type.
Yep.
But just having the code isn't enough to, like the error code tells you that there's a found and expected type, but it still doesn't tell you. It doesn't tell you what the expected type is without using a regular expression, and the compiler might change this formatting. So it seems like we still need something to pass this information along.
Yeah, exactly. So like it's sort of a half win, right? Because in that scenario, the compiler at that point in time knows not how to fix it necessarily, but it knows what the return type is, and it knows what the expected type is. So we can use a unique identifier to know that that's the error, but we don't have that extra information to apply the fix. So like stretch goal would be kind of what we talked about this yesterday, but having a structured way to return that data as well. So in the scenario you just referenced, we would have an error message saying there's a mismatch type here at this position. Here's the unique identifier for you to know exactly that this is the error. And then here's some extra data and another position to know that this is how you would fix it, is you would switch this annotated type from a string to an int, for example.
Yeah. So I think you need like a way to pass arbitrary data along the whole chain you showed. So you need basically to pass JSON from the compiler to the...
Absolutely. I don't want to undersell that it's not like a huge change that would need to happen all the way from the compiler, through the interfaces, through the build tools, through like the report, like everywhere basically. But the nice thing is that from Zinc, or rather from BSP all the way down to your editor, it's already implemented. So in that case, the real change needs to just happen in the compiler, because the rest of the tool chain knows how to actually handle these things already. It knows how to handle the extra data, knows how to apply these fixes. So it's up to the compiler team, like you, I'm just kidding, to make these changes, yeah. Okay, no more time for questions, but I will be outside if anybody wants to chat about this or metals or any other tooling related stuff. So thanks.